You are currently blind to almost everything happening around you. While the mathematics describing electromagnetic radiation prove that the universe is saturated with energy in every direction. At every moment, your brain grants you conscious access to only the thinnest possible sliver of that reality. Somewhere between the perfect, infinite equations that describe how light behaves and the biological machinery sitting behind your eyes, an almost unimaginable amount of information simply disappears. It does not get stored somewhere for later. It does not get compressed into a smaller file you could decode with effort. It vanishes, filtered out before it ever reaches the part of you that thinks of itself as aware. And the strange part is that you have never noticed, because the very system doing the filtering is also the system that convinces you nothing is missing. Picture the electromagnetic spectrum as an ocean that stretches farther than the mind can comfortably hold. On one end sit radio waves, some stretching 4 kilometers from crest to crest, humming through walls, mountains, and the vacuum of space with almost no resistance. On the other end sit gamma rays, waves so short and so energetic that a single one can tear through the bonds holding atoms together. Between those two extremes lies every frequency of microwave that cooks your food and carries your phone calls. Every band of infrared that pours off a warm body in the dark. Every wavelength of ultraviolet that a bee uses to navigate a flower. And every burst of X-ray radiation that a hospital machine uses to see through skin and muscle to bone. Somewhere in the middle of that entire ocean, occupying a band so narrow it barely deserves to be called a fraction, sits the visible spectrum. This is the only part of the electromagnetic ocean your unaided eyes were ever built to detect. And it represents such a small portion of the whole that if the entire spectrum was stretched across the length of a continent, the visible portion would occupy a strip you could step over without noticing. Modern imaging technology has made this invisible ocean impossible to ignore. Satellites now orbiting the planet carry instruments tuned to frequencies far outside anything a human retina could register. And the pictures they return are nothing like the calm blue marble most people picture when they imagine Earth from space. In infrared, cities do not look like clusters of grey concrete. They glow like scattered embers, radiating the heat trapped in asphalt and steel long after the sun has set. In microwave and radio bands, the sky is not empty and silent. It hums with a faint, almost uniform static left over from the earliest moments after the Big Bang. A signal so ancient that by the time it reaches a detector, it has traveled for more than 13 billion years. In ultraviolet, the sun does not look like a smooth yellow disk. It looks like a churning, violent surface pocked with looping magnetic storms far larger than the planet itself. None of this is new physics. Every one of these signals has been present the entire time you've been alive. What changed is that instruments were finally built sensitive enough and patient enough to listen to frequencies your own senses were never designed to hear. This sets up one of the strangest tensions in modern science. A tension between two things that are both, in their own way, completely correct. On one side sits the mathematics of electromagnetism, a set of equations so elegant and so consistently accurate that engineers use them to build everything from television broadcasts to satellite navigation, without ever needing to question whether the underlying theory might be wrong. These equations describe light as a continuous wave, oscillating electric and magnetic fields locked together, propagating through space at a fixed, unbreakable speed, spanning every frequency without gap or preference. On the other side sits biology, an evolutionary process that never once tried to build a sensor capable of detecting that entire range. Biology built something far more modest and far more selective, an organ optimized not to reveal truth, but to keep an animal alive long enough to reproduce. Reconciling these two things, the infinite mathematical reality of the wave and the narrow biological reality of the eye, is not simply an academic exercise. It forces a direct confrontation with a question that sounds almost philosophical but is, in fact, deeply physical. What does it actually mean to see reality, when the very organ doing the seeing was built to filter almost all of it out? Before that confrontation can happen, the wave itself needs to be understood on its own terms, stripped of any assumption about what a human eye is capable of noticing. In the 1860s, a Scottish physicist working through a set of scattered discoveries about electricity and magnetism realized something that nobody had fully grasped before him. Electric fields and magnetic fields were not two separate phenomena that happened to share a name. They were two expressions of a single underlying field. And when that field oscillated in the right way, it produced a wave capable of carrying energy through empty space without needing any medium to travel through at all. This was a radical claim at the time. Sound needs air. Water waves need water. Every wave anyone had previously studied needed some physical substance to ripple through. But when the mathematics were worked out fully, they predicted a wave that needed nothing. A self-sustaining oscillation where a changing electric field generates a changing magnetic field, which in turn generates a changing electric field, endlessly regenerating itself as it moves forward at a single, fixed speed. When that speed was calculated from the equations alone, using constants that had already been measured in laboratory experiments involving nothing but electricity and magnetism, the number that came out matched, almost exactly, a completely different number that had already been measured by astronomers studying the speed of light. It was one of those rare moments in science where two entirely separate lines of investigation collided and revealed that they had, without anyone realizing it, been describing the exact same phenomenon the entire time. Light was not some mysterious substance that behaved according to its own private rules. Light was an electromagnetic wave, and every electromagnetic wave, whether it carried a radio broadcast or a beam of visible sunlight, obeyed the exact same equations. This discovery did something remarkable to the boundaries of what counted as light. Once light and electromagnetism were unified into a single phenomenon, there was no longer any physical reason to treat the narrow visible band as special. A radio wave and a beam of green light differ only in wavelength and frequency, not in fundamental nature. They are both disturbances in the same field, both traveling at the same universal speed, both fully described by the same set of equations. The only thing separating a radio station's broadcast from the light reflecting off a leaf is how tightly the wave is compressed, how rapidly it oscillates as it moves. This means the electromagnetic spectrum is not a collection of different types of energy loosely related to one another. It is a single continuous phenomenon, sliced only by an arbitrary human convenience of measurement, stretching without any natural boundary from the longest radio waves to the shortest gamma rays. If the physics places no special importance on the visible range, then the fact that living organisms became sensitive almost exclusively to that range demands an explanation, rooted not in the properties of light itself, but in the properties of the environment those organisms evolved inside. The sun does not emit its energy evenly across the electromagnetic spectrum. It emits a curve, a distribution that peaks sharply in a specific band and tapers off on either side. That peak happens to sit almost exactly where the human visible range sits, which is not a coincidence but a consequence of the fact that eyes evolved on a planet bathed in that particular curve of light. An eye tuned to a wavelength the sun barely emits would be an eye starved of signal, straining to detect a faint trickle of photons in a world flooded with abundance just outside its range. Earth's atmosphere adds a second filter on top of the sun's own output. Water vapor, oxygen, and ozone absorb huge portions of the incoming electromagnetic spectrum before it ever reaches the ground, blocking most ultraviolet and effectively all X-ray and gamma-ray radiation, while leaving a relatively clear window open in the visible range and parts of the infrared and radio bands. Any eye evolving on the surface of this particular planet was, in effect, evolving inside a narrow atmospheric window, and it makes evolutionary sense that vision would specialize to exploit the band, where photons were both abundant from the sun and unobstructed by the sky above. There is also a practical engineering constraint buried inside the physics of very short and very long wavelengths that further narrows the useful range for a biological detector. Wavelengths much shorter than visible light, such as ultraviolet, X-ray, and gamma radiation, carry enough energy per photon to damage the delicate molecular machinery of living tissue, breaking chemical bonds and mutating genetic material rather than gently triggering a signal. Building an eye sensitive to those wavelengths would mean building an eye that slowly destroys itself every time it is used. Wavelengths much longer than visible light, such as infrared, microwave, and radio, carry too little energy per photon to reliably trigger the kind of chemical reaction a biological photoreceptor depends on. And they also require enormous detector structures to focus and resolve, since the physical size of a receiving structure needs to be comparable to the wavelength it detects in order to gather it efficiently. A radio wave with a wavelength longer than a house cannot be meaningfully focused by an organ the size of a human eyeball. Visible light sits in a rare sweet spot, energetic enough to trigger fast, reversible chemical changes in a photoreceptor without breaking it apart, and short enough in wavelength to be focused with reasonable precision by a lens only a few centimeters across. Evolution did not choose the visible spectrum out of some abstract preference. It converged on the visible spectrum because that band was, for a carbon-based organism living under this particular star behind this particular atmosphere, the only band where a functional, appropriately sized eye was physically achievable at all. None of this changes the fact that the moment has come to look directly at what happens once a photon of visible light actually strikes a living eye, because this is the point where an elegant, infinite, mathematically perfect wave collides with the messy, finite, biologically constrained machinery of a nervous system, and the collision is where the real story of perception begins. At the back of the human eye sits a thin layer of tissue called the retina, and embedded within that layer are two broad categories of specialized cells built for one purpose: catching photons and converting them into an electrical signal a nervous system can actually use. The first category, called rods, are extraordinarily sensitive to light but register no information about wavelength at all, contributing almost entirely to vision in dim conditions and to peripheral awareness rather than sharp, colorful detail. The second category, called cones, are the cells actually responsible for color vision. And in a typical human eye, there are three distinct types of cone, each built around a slightly different version of a light-sensitive pigment protein that responds. most strongly to a particular range of wavelengths, loosely corresponding to what would later be labeled red, green, and blue. When a photon strikes one of these pigment molecules, it triggers a rapid structural change in the molecule's shape, and that shape change sets off a cascade of chemical reactions inside the cell that ultimately produces an electrical signal. This is the exact moment where the wave stops being a wave. A photon arriving at the retina carries a precise, continuous wavelength, some exact value that could in principle be measured to arbitrary precision by a sufficiently sensitive instrument. The cone cell that absorbs it does not preserve that precision. It does not pass along the wavelength as a number. It converts the event into a simple, binary adjacent signal. This particular type of cone fired, or it did not, and it fired with roughly this much intensity. 3 overlapping curves of sensitivity, 3 rough categories of chemical response, is the entire data set the human eye ever sends onward into the brain. Every one of the millions of distinguishable colors a person can consciously perceive is reconstructed afterward, in the visual cortex, from nothing more than the relative firing ratios of 3 broad, overlapping types of receptor. The brain is not receiving a faithful readout of the electromagnetic spectrum. It is receiving 3 crude dials, and everything people call color is a story woven from the position of those 3 dials alone. This is the bottleneck at the heart of the entire paradox. An electromagnetic wave carrying information across a theoretically continuous and infinite range of possible frequencies gets funneled, at the exact moment of biological contact, into a system with only 3 effective input channels. Compare this to modern spectrometers, laboratory instruments capable of resolving light into hundreds or even thousands of distinct wavelength bins, producing a detailed fingerprint of exactly which frequencies are present and in what proportion. A spectrometer pointed at a beam of light and a human eye pointed at the same beam are technically responding to the same physical phenomenon, but the amount of information each one extracts from it is almost comically different. The eye is not a weak spectrometer. It is not even attempting the same task. It abandoned the goal of measuring wavelength precisely a very long time ago, in favor of a completely different goal, producing, as quickly and cheaply as possible, a signal useful enough to help an organism find food, avoid predators, and recognize a mate. The transition from physics to biology, then, is not simply a transition from one kind of data to another. It is a transition in purpose. The wave itself has no goal. It simply propagates according to the equations that govern it, indifferent to whether anything is watching. The eye, by contrast, was shaped entirely by goals, sculpted over hundreds of millions of years by the relentless pressure of survival. And survival never once required an accurate readout of the electromagnetic spectrum. It required speed, reliability, and just enough discrimination to tell a ripe fruit from an unripe one, or a predator's shape from a shadow. Understanding color, then, means setting aside the assumption that color is a property of light at all, and instead treating it as a product, manufactured entirely inside a nervous system. If you have ever wondered how much of what you consider solid, external reality is actually being assembled behind your own eyes, rather than delivered ready-made from the world outside, this is exactly the kind of question worth sitting with for a moment before continuing, because the deeper this investigation goes, the more that boundary between the observer and the observed starts to blur. Color feels like one of the most objective, undeniable features of the world. A red apple looks red whether you are 8 years old or 80. Whether you learned the word for it in one language or another, and that consistency creates a powerful, almost unshakable intuition that redness is a property sitting out there in the apple itself, waiting to be detected. But the physics tells a different story. The surface of the apple is not producing red light in any special sense. It is simply reflecting a broad mixture of wavelengths while absorbing others. And the particular mixture it reflects happens to stimulate the long wavelength cones in a human retina more strongly than the other two types. Change the observer, and the apple stops being red at all. A dog, lacking a functional third cone type, would see the same apple rendered in a duller, more muted palette, unable to distinguish it clearly from certain shades of green. A mantis shrimp, equipped with as many as a dozen or more distinct types of photoreceptor, depending on the species, would perceive that same apple through a dimension of color complexity no human visual system could even represent, let alone imagine. The apple has not changed. The light bouncing off its surface has not changed. Only the biological instrument doing the interpreting has changed. And yet the resulting experience of color is entirely different in each case. This single thought experiment dismantles the intuition that color is an intrinsic property of objects. Color is a relationship, constructed jointly by a light source, a reflecting surface, and a nervous system. And it exists nowhere in that chain except inside the nervous system itself. Neuroimaging research conducted in recent years has pushed this understanding even further, tracing color perception not just to the retina but deep into the layered processing of the visual cortex, where signals from the three cone types are compared, subtracted, and recombined through what researchers call opponent processing, rather than simply reporting three raw intensity values. The visual system computes differences. How much more red-sensitive signal is present compared to green-sensitive signal? How much more blue-sensitive signal is present compared to a combined red and green baseline? These computed differences are what actually get passed forward into conscious perception, which explains a number of strange and highly specific quirks of human vision, such as why staring at a bright red image for an extended period and then looking away produces a ghostly green afterimage, or why certain colors seem to feel like inherent opposites, like red and green or blue and yellow, while others do not carry that same oppositional quality. These are not artifacts of the physical world. They are artifacts of how the nervous system chose to encode a small number of signals as efficiently as possible, favoring contrast and difference over raw, redundant intensity. Because contrast is what actually helps distinguish one object's edge from another's in a cluttered visual scene. The deeper implication is that evolution never optimized vision for accuracy in any abstract, philosophical sense. It optimized vision for usefulness, and usefulness is a radically different design target than truth. A visual system that faithfully reported every wavelength present in a scene, down to fine spectral detail, would be drowning its owner in far more data than could ever be processed quickly enough to dodge a predator or catch a moving target. Evolution instead favored a system that discarded almost everything and kept only the small number of signals, reliably correlated with survival-relevant features, edges, motion, the boundary between ripe and unripe, the boundary between skin flushed with blood and skin that is not. Three cone types, compressed through opponent processing, turned out to be enough to solve those specific problems reliably. And once that threshold of enough was reached, there was no evolutionary pressure pushing toward anything more elaborate, because building and maintaining a more complex visual system carries, a real biological cost in energy and neural tissue that only pays off if it improves survival or reproduction. A four-color visual system, of the kind found in birds and some reptiles, that can detect ultraviolet in addition to the 3 human visible bands, exists precisely because ultraviolet reflectance patterns on feathers, flowers, and fruit carry genuinely useful survival and mating information for those particular species. Humans never needed that 4th channel badly enough to justify carrying it, so the lineage that led to modern humans lost the 4th cone type at some point in its evolutionary past, trading a wider window on reality for a cheaper, sufficient one. This raises an uncomfortable but genuinely important question. If the visual system was never built to reveal an accurate picture of the electromagnetic environment, and was instead built purely to be useful, then what would it even mean to ask what the world truly looks like? The question assumes there is some neutral, observer-independent version of looking, some view from nowhere that could be compared against the human view to measure how accurate or inaccurate it is. But every conceivable way of looking requires a detector of some kind, and every detector, biological or artificial, has to make choices about what to keep and what to discard, because no detector, however advanced, can register the entire infinite electromagnetic spectrum with equal fidelity at every possible frequency simultaneously. A spectrometer captures wavelength with extraordinary precision but tells you nothing about spatial layout. A camera captures spatial layout with extraordinary precision but usually compresses wavelength into only 3 or 4 broad channels. Not unlike the human eye itself, every act of perception, biological or mechanical, is necessarily a form of translation, and every translation involves loss. The idea of a complete, unfiltered, perfectly accurate view of reality may not simply be biologically unavailable to humans. It may be a concept that does not coherently exist for any finite observer of any kind. Anywhere. That does not mean all forms of perception are equally limited, however. And this is where the conversation moves from abstract philosophy back into concrete, testable science. Because while the biological human eye is permanently fixed at 3 narrow channels by the hard constraints of its evolutionary history, technology is not bound by those same constraints. And researchers have spent the last several years building tools that quietly begin to extend human perception past the boundary. Biology drew for it. The most direct approach researchers have taken to expanding human sensory range is simple in concept, even when it is difficult in execution. Take a frequency the human body cannot detect on its own. Use an artificial sensor to capture it, and then translate that captured signal into a channel the body can already interpret. Whether that channel is vision, hearing, or touch. Thermal cameras have existed in various forms for decades, converting infrared radiation, the heat signature every warm object constantly emits, into a false color visible image a human eye can read directly. What has changed more recently is the miniaturization and integration of this kind of sensing into wearable devices, moving thermal perception out of bulky, specialized equipment and into something closer to an accessory a person might wear throughout an ordinary day, quietly overlaying a layer of infrared information onto an otherwise normal visual field. Wearing such a device does something genuinely strange to a person's sense of their surroundings. A wall that looks featureless in ordinary light reveals the ghostly outline of pipes running behind the plaster, warmed slightly by the water moving through them. A parked car that looks cold and inert reveals the recent memory of its own engine, glowing faintly where heat has not yet fully dissipated. None of this information was ever hidden or secret. It was radiating outward the entire time, indifferent to whether anyone was equipped to notice it. A separate and increasingly active line of research involves sensory substitution, a technique where information from an entirely different part of the electromagnetic or physical spectrum is translated, not into vision but into touch or sound, allowing the brain's remarkable capacity for neural plasticity to gradually learn to interpret a completely novel channel of input as though it were a native sense. Devices have been developed that convert magnetic field orientation into a continuous vibration on a wearer's skin, effectively granting a crude, always-on sense of magnetic north, similar in principle to the magnetoreception known to exist in birds and some other migratory animals. Other experimental systems convert Wi-Fi signal strength and density into an audible tone, allowing a wearer to, in effect, hear the invisible mesh of wireless data constantly flooding through the walls of any modern building. What researchers have consistently found in these experiments is that the brain does not treat this new information as an abstract, effortful calculation for very long. After a period of adjustment that can range from days to a few weeks, the translated signal begins to feel less like data being consciously interpreted and more like a direct, intuitive perception integrated into the wearer's ongoing sense of their environment with surprisingly little friction. The nervous system, it turns out, is not narrowly hardwired to only ever process the specific handful of channels biology originally provided. It is a remarkably general-purpose signal processor, willing to adopt an entirely new sense so long as it is delivered in a format the existing neural architecture can work with. More invasive approaches are being explored as well, particularly in the context of neural implant research. Originally developed to restore sight to people with certain forms of blindness, these systems typically work by bypassing a damaged or not functional eye entirely and delivering electrical stimulation directly to the visual processing regions of the brain, based on data captured by an external camera. Because the system does not depend on a biological eye at all, the external camera can, in principle, be tuned to capture wavelengths far outside the narrow, visible band humans naturally perceive, whether that means infrared, ultraviolet, or even artificially constructed representations of other electromagnetic bands entirely. Early research in this space remains focused primarily on restoring basic functional vision for people who have lost it, rather than granting expanded vision to people who already see normally. But the underlying architecture raises a genuinely open question that researchers in the field openly discuss: if a camera can be tuned to any wavelength, and a neural interface can deliver that data directly into visual processing regions of the brain, there is no fundamental technical reason why a future version of this technology could not eventually offer expanded spectral vision to anyone willing to use it, not just those who need it to restore lost function. The psychological dimension of all this deserves just as much attention as the engineering, because expanding perception is not simply a matter of adding more information. It changes the felt texture of ordinary experience in ways that are difficult to anticipate in advance. People who have used extended sensory devices for meaningful stretches of time report a consistent and somewhat disorienting effect. Previously invisible aspects of the environment begin to feel less like abstract facts learned from a textbook and more like directly, viscerally present features of the world, impossible to unnotice once the new sense has become familiar. A room that once felt calm and static, once its invisible wireless traffic becomes audible, can begin to feel busy, layered, even faintly crowded, despite looking exactly the same to unaided vision. A person standing near a cell tower or a running appliance may develop a genuinely new, embodied sense of electromagnetic density in their environment, similar to the way most people already have an intuitive, effortless sense of how loud a room is or how bright it is, except applied to a domain of the electromagnetic spectrum they had no prior sense for at all. This suggests that the boundary of what counts as a normal, felt aspect of reality is not fixed by biology alone. It is fixed by whichever channels a given nervous system happens to have been trained to interpret. And that training window, it turns out, remains open for far longer into adulthood than most people assume, and may never fully close. Considered together, these developments point towards something larger than a simple list of clever gadgets. They point toward the electromagnetic spectrum itself functioning as a kind of permanent, ever-present layer of information sitting just outside conscious human awareness. Not because it is inaccessible in any deep sense, but because biological evolution never had a reason to grant unaided access to it. Every one of these technologies works by doing exactly what the eye already does, translating a physical signal into a format a nervous system can use, except doing it for frequencies the eye itself was never built to touch. In that sense, none of this represents some radical departure from how perception has always worked. It represents an extension of the exact same principle biology already relies on, applied to a wider slice of the same infinite ocean of electromagnetic energy that has been surrounding every living creature on this planet, since long before any nervous system existed to notice it at all, long before satellites or neural implants. The first hints that light extended beyond what the eye could see arrived through a much simpler experiment, one that any careful observer could have stumbled upon with nothing more than a prism, a sheet of paper, and a thermometer. In the early 1800s, an astronomer already famous for discovering a new planet turned his attention to a much smaller, more overlooked question: whether sunlight passed through a prism carried heat evenly across the visible rainbow it produced, or whether some colors carried more warmth than others. He placed thermometers along the spread-out band of colors, violet on one end, red on the other, and measured a small but consistent rise in temperature as he moved from violet toward red. Then, almost as an afterthought, he placed a thermometer just past the red edge of the visible band, in the region where no color was visible to the eye at all, expecting to find nothing meaningful there. Instead, the temperature reading climbed even higher than anywhere within the visible spectrum itself. Something was there, carrying energy, warming the thermometer, despite being completely invisible. He had discovered what would later be named infrared radiation, and he had discovered it not by seeing it, but by feeling its effect on an instrument sensitive to a property, heat, that the eye itself cannot directly perceive at all. Word of this discovery spread quickly through the scientific community, and within roughly a year, a chemist working with the opposite end of the visible spectrum wondered whether a similar invisible extension might exist past violet as well. Rather than measuring heat, he used a chemical approach, treating paper with silver salts, known to darken when exposed to light. He placed strips of this treated paper at various points along the visible spectrum and beyond, and found that the paper darkened even in the region just past violet, where, again, nothing was visible to the unaided eye at all. In fact, the paper darkened there more quickly than it did anywhere within the visible spectrum itself, revealing an entirely separate, invisible band on the opposite side of human vision from the one just discovered a year earlier. This region would eventually be named ultraviolet, and its discovery, paired with the discovery of infrared just months before, effectively proved for the first time that the human eye was not detecting the totality of light. It was detecting a bounded, finite window sitting between two invisible neighbors, each one just as physically real and just as full of measurable energy as the colors any person could actually see. These two 19th century discoveries mark the moment the boundary of human perception first became scientifically visible as a boundary, rather than simply being assumed to be the entirety of what light was. Every subsequent expansion of the known electromagnetic spectrum, from the discovery of radio waves through experiments with oscillating electrical circuits, to the accidental discovery of X-rays while studying the glow produced by vacuum tubes, to the identification of gamma radiation emerging from the newly discovered phenomena of radioactivity, followed the same basic pattern established by those first infrared and ultraviolet experiments. Each time, an instrument, rather than an eye, was the thing that first noticed the invisible signal, and each time, the discovery quietly expanded the known size of the electromagnetic ocean while leaving the size of the human visible window exactly as small as it had always been. By the early 20th century, physicists had assembled something close to the modern picture of the full spectrum. A picture in which the visible band occupies such a disproportionately small fraction of the whole that its narrowness became, for many physicists, one of the most quietly astonishing facts in all of physics, hiding in plain sight behind something as mundane and familiar as the act of seeing. Around the same period, this expanding map of the spectrum was being assembled. Physicists ran headlong into an entirely separate puzzle about the fundamental nature of light itself, one that added a further layer of strangeness to the story of perception. Experiments studying how light interacts with metal surfaces revealed that light does not always behave as a smooth, continuous wave, the way Maxwell's equations had so successfully described it. Under certain conditions, light behaves instead as though it arrives in discrete packets, individual units of energy later named photons, each one carrying an amount of energy directly tied to its frequency rather than spread continuously across space. This discovery, developed further through the early decades of quantum theory, revealed that light possesses what physicists call wave-particle duality, behaving like a continuous wave in some experiments and like a stream of discrete particles in others, with neither description alone being sufficient to capture everything light actually does. This duality is not some minor technical footnote. It sits at the very foundation of how a photon striking a cone cell in the retina actually triggers a signal in the first place, because it is the particle-like, discrete nature of a photon's energy that allows a single quantum of light to trigger a single threshold-crossing chemical event inside a photoreceptor molecule, rather than requiring a smoothly building, continuous wave to slowly accumulate before anything happens at all. In an important sense, human vision itself is a quantum process, built on the fact that light comes in indivisible packets, small enough and energetic enough to flip a single molecular switch, one photon at a time. This quantum foundation adds an extra layer of humility to the entire discussion of perception, because it reveals that even the visible light a human eye successfully detects is not being perceived in some smooth, complete, continuous fashion either. At the level of individual photoreceptor cells, vision is fundamentally a statistical, probabilistic process, built from an enormous number of discrete, quantum-scale detection events that the brain smooths together into what feels like a continuous, unbroken visual experience. Even within the narrow band of light a human can see, the underlying physical reality is grainy, particle-based and probabilistic, and the sense of smooth, effortless continuity that vision provides is itself another layer of construction. Another translation performed by a nervous system determined to present a usable, coherent picture regardless of the machines of the raw data feeding into it. Stepping back from the human case entirely and looking across the animal kingdom reveals just how many independent solutions evolution has produced to the basic problem of sensing the electromagnetic environment. Each solution shaped by the specific survival pressures facing a particular lineage rather than by any universal standard of what counts as complete or accurate perception. Certain species of pit vipers possess specialized organs on their faces containing a thin membrane packed with heat-sensitive nerve endings, allowing the snake to detect infrared radiation emitted by a warm-blooded prey animal with enough precision to strike accurately in complete darkness, using a sense with no equivalent anywhere in human physiology. Migratory birds appear to rely on a form of magnetoreception, a still not fully understood ability to detect the orientation of Earth's magnetic field, possibly mediated by light-sensitive proteins in the retina that respond differently depending on magnetic alignment, effectively fusing a magnetic sense directly into the visual system itself in a way that has no clean analog in human biology at all. Certain species of fish that live in murky, low-visibility water have evolved electroreception, generating a weak electric field around their own bodies and sensing distortions in that field caused by nearby objects. A sensory strategy that has nothing to do with light at all and instead exploits an entirely different physical phenomenon to build a working model of the immediate environment. And the mantis shrimp, already mentioned for its unusually large number of distinct photoreceptor types, appears to process color information through an entirely different neural strategy than most other animals, potentially trading fine color discrimination for exceptional speed of processing. Since research suggests its visual system may prioritize rapid identification over refined comparison, a strategy well suited to a predator that strikes with such explosive speed that timing matters more than nuance. Taken together, this comparative picture makes an important point unmistakably clear. There is no single correct or complete way to perceive the electromagnetic environment, only a wide diversity of partial, task-specific solutions, each one shaped by the particular ecological pressures facing a particular species. The human visual system is neither the most sophisticated nor the most limited entry in this catalogue. It is simply one more specialized solution among many, tuned to the particular challenges faced by a primate lineage that needed to spot ripe fruit, recognize faces, judge distances while moving through three-dimensional environments like trees and open grassland, and do all of this using a brain that also had to remain small and energy efficient enough to be biologically sustainable. Judged against that specific set of ancestral tasks, human color vision is, in fact, remarkably well designed. Judged against the full scope of the electromagnetic spectrum, it is almost vanishingly narrow. Both of those statements are true at the same time, and reconciling them requires abandoning the idea that there is some single, objective scale of perceptual completeness against which every visual system should be measured. This comparative picture leads, naturally, into one of the oldest and most stubborn questions in the philosophy of mind. A question that becomes almost unavoidable once the biological machinery of color has been laid out this plainly. If color is manufactured by a nervous system rather than delivered ready-made from the external world, what is actually happening at the moment a person consciously experiences the redness of red? There is a difference between describing the physical chain of events, a photon striking a cone cell, a cascade of chemical reactions, an electrical signal traveling along a nerve, a pattern of activity distributed across the visual cortex, and describing the subjective feeling of seeing red itself, the qualitative, felt character of the experience from the inside. Philosophers refer to this felt, qualitative character using the term qualia, and the persistent difficulty of explaining how or why any particular pattern of neural activity should be accompanied by a subjective feeling at all, rather than simply happening in the dark with no experience attached, has come to be known among researchers as the hard problem of consciousness, a label chosen specifically to distinguish it from the comparatively easier, though still difficult, task of mapping which neurons fire in which sequence during a given perceptual event. This is not a question. Modern neuroscience currently has a settled answer to, and it is important to be honest about that, rather than gesturing toward some future discovery as though the matter were already resolved. Researchers have made extraordinary progress mapping the physical correlates of color perception, identifying with increasing precision which regions of the brain become active during specific visual experiences, and even beginning to predict, with reasonable accuracy, what someone is looking at based purely on patterns of brain activity recorded during an experiment. But identifying the physical correlate of an experience is not the same as explaining why that physical process is accompanied by any subjective experience at all, rather than occurring as what philosophers sometimes describe as a kind of unconscious information processing with no inner feeling attached to it whatsoever. This gap between physical description and subjective experience remains genuinely open, discussed and debated across neuroscience, philosophy, and cognitive science, without anything resembling scientific consensus on how, or even whether, it will eventually be closed. What can be said with much greater confidence, because it follows directly from established, well-tested science rather than from open philosophical debate, is that whatever the subjective experience of color actually is, it is being constructed from an extraordinarily narrow slice of available physical information. The hard problem of consciousness asks why there is a felt quality to experience at all. The photon perception paradox asks a related but distinct question. Given that there is a felt quality to experience, why is the raw material feeding into that experience so radically filtered before it ever reaches the point of becoming conscious? These two questions, though often discussed together, do not require the same answer, and it is worth being careful not to blur them together. A person could, in principle, imagine a nervous system that processed the entire electromagnetic spectrum with perfect fidelity, and still faced exactly the same open puzzle about why any of that processing produces subjective experience in the first place. Equally, a person could imagine a nervous system that produced no subjective experience at all, and yet still filtered its input down to a narrow, survival-relevant slice of the electromagnetic spectrum for the exact same evolutionary reasons already discussed. The narrowness of perception and the mystery of subjective experience are two separate puzzles that happen to intersect inside the same organ, and untangling them carefully is part of what makes this such a genuinely difficult area of both science and philosophy to think through clearly. There is a further complication worth sitting with honestly, one that becomes obvious the moment two people try to compare their subjective color experiences directly. There is currently no known experiment capable of confirming that two different people experience the same wavelength of light in the same subjective way, even when both people apply the identical word to describe it. Both might learn to call a particular wavelength red as children. Both might use that word consistently and correctly for the rest of their lives. Both might even show extremely similar patterns of brain activity when viewing that wavelength. And yet there remains, at least with current scientific tools, no way to directly compare the raw, private, felt quality of what each person is actually experiencing when that word is used. This possibility, sometimes referred to as the inverted spectrum problem, illustrates just how much of ordinary human communication about perception rests on behavioral agreement, consistent labeling, and consistent responses, rather than on any confirmed, verified sameness of inner experience. It is a humbling thought, and one that fits naturally into everything already established about the constructed, filtered, translated nature of color. Not only is human color perception a narrow slice of a much larger electromagnetic reality, it may also be, in its deepest subjective character, a private experience that even two people standing side by side, looking at the exact same object, can never fully confirm they share. None of this uncertainty should be mistaken for an excuse to treat the science of perception as unsettled or unreliable in a broader sense. The physical chain of events from photon to retina to nerve signal to cortical processing is understood with remarkable precision, confirmed across decades of careful experimentation, and it is that well-established physical chain, rather than the unresolved philosophical questions sitting at its far end, that actually explains why the electromagnetic spectrum experienced by a human being is so much smaller than the electromagnetic spectrum that physically exists. The philosophy adds depth and humility to the picture. It does not undermine the underlying physics and biology, which remains solidly established regardless of how the harder philosophical puzzles eventually get resolved, if they ever fully do. Setting the deepest philosophical questions aside for a moment, there remains a substantial and very active body of ongoing scientific research directly focused on the narrower, more tractable puzzle of how sensory systems filter information. And this research continues to reveal new and sometimes unexpected details about a process long assumed to be fully understood. Researchers studying the genetics of color vision have identified naturally occurring variations in the genes responsible for cone pigment proteins, variations that produce measurable shifts in exactly which wavelengths a given person's cones respond to most strongly. In rare cases, some individuals, almost always women, due to the specific way these genes are inherited on the X chromosome, carry an unusual genetic combination that appears to grant them for functional cone types instead of the typical three, a condition researchers refer to as tetrachromacy. Behavioral testing on a small number of confirmed tetrachromats suggests that at least some of these individuals can reliably distinguish between pairs of colors that appear completely identical to a standard three-cone observer, offering a rare, real-world glimpse of what a modest, biologically native expansion of human color perception might actually look and feel like, hiding in plain sight within the existing human population rather than requiring any external technology at all. Other researchers have focused less on individual variation and more on how perceptual filtering itself might be adjusted or trained through deliberate practice and prolonged exposure. Building on the same neural plasticity that makes sensory substitution devices effective in the first place, studies involving individuals who spend extended periods wearing color filtering equipment, deliberately altering which wavelengths reach their eyes, have found that the visual system gradually recalibrates its sense of what counts as a neutral, natural range of color, adjusting the internal reference points used for comparison, even without any change to the underlying hardware of the eye itself. This kind of research reinforces a theme that runs through nearly every corner of the science of perception discussed. So far, the boundary of what a nervous system treats as normal, complete, or natural is far more flexible and far more shaped by ongoing calibration than most people intuitively assume. And that flexibility appears to persist to some meaningful degree throughout adult life, not merely during the more commonly discussed periods of early childhood development, when the brain is known to be at its most adaptable, beyond the boundary of any single human body. An entirely separate and vastly more powerful expansion of perception has been unfolding at the level of human civilization as a whole, carried out not through implants or wearable devices, but through the construction of instruments capable of gathering electromagnetic information across bands no individual eye could ever hope to access, and then translating that information into forms a human mind can study, interpret, and reason about collectively. Radio telescopes, arrays of enormous dish antennas spread across vast stretches of open landscape, have spent decades listening to the universe in wavelengths measured in centimeters and meters, rather than the tiny fractions of a micron that define visible light, revealing entire categories of astronomical phenomena that remain completely invisible to any optical telescope, no matter how powerful. Pulsars, the rapidly spinning collapsed cores of dead stars, sweeping narrow beams of radio energy across space like a cosmic lighthouse, were first identified not through any visual sighting, but through the detection of a startlingly regular radio pulse, so precise and so mechanical in its timing that the researchers who first found it briefly wondered whether they had accidentally intercepted a signal from an intelligent civilization before the natural explanation was confirmed. Infrared observation has proven similarly essential for seeing through obstacles that block visible light entirely. Thick clouds of interstellar gas and dust, the very nurseries where new stars and planetary systems are born, are almost completely opaque to visible light, hiding the earliest and most formative stages of stellar formation from any purely optical telescope. Infrared radiation, with its longer wavelength, passes through that same dust far more easily, allowing infrared-equipped observatories to peer directly into the heart of these stellar nurseries and watch young stars, still in the process of gathering material from the surrounding cloud, a process that would otherwise be entirely hidden from view. The most advanced infrared space observatory currently operating, positioned far from Earth to keep its own instruments extremely cold and free from interference, has spent recent years using exactly this capability to observe some of the earliest galaxies known to have formed after the Big Bang, their visible light stretched by the expansion of the universe itself into wavelengths so long that only an infrared-sensitive instrument could ever hope to detect them at all. In a very real sense, this observatory functions as a kind of technological retina built specifically to solve the same fundamental problem discussed throughout this entire investigation. Extending perception beyond the narrow-band biology alone could ever provide, in order to reveal a portion of physical reality that would otherwise remain permanently and completely invisible. X-ray and gamma-ray astronomy push this same principle even further, requiring instruments launched above Earth's atmosphere entirely, since the atmosphere itself absorbs these high-energy wavelengths before they ever reach the ground, which is fortunate for biological life but deeply inconvenient for anyone hoping to study the extraordinarily violent processes in the universe that emit them. Matter spiraling into a black hole, superheated to temperatures of millions of degrees by the immense gravitational forces tearing it apart before it crosses the point of no return, radiates the overwhelming majority of its energy in X-rays rather than visible light, meaning that many of the most energetic and dramatic events in the observable universe would remain completely undetected by any instrument limited to the visible spectrum alone. Gamma-ray bursts, the single most energetic explosions known to occur anywhere in the universe since the Big Bang itself, release more energy in a matter of seconds than an entire galaxy releases over vastly longer timescales. And these bursts are, by their very nature, defined and detected almost entirely through gamma radiation, a portion of the spectrum so far removed from anything a biological eye evolved to sense that without dedicated instrumentation, humanity's entire species would have remained completely unaware that such catastrophically energetic events were even occurring anywhere in the cosmos at all. Perhaps the most striking recent illustration of how narrow biological perception truly is compared to the full scope of physical phenomena worth detecting comes from an entirely different category of instrument, one that does not measure electromagnetic radiation at all. Gravitational wave detectors, first achieving a confirmed direct detection only in the past decade, measure ripples in the fabric of space-time itself, produced by cataclysmic events such as the collision of two black holes or two neutron stars. Ripples so faint by the time they reach Earth that the instruments built to detect them must measure a change in distance many thousands of times, smaller than the width of a single proton. These ripples carry no electromagnetic signal whatsoever, meaning that no possible expansion of any eye, biological or artificial, tuned to any portion of the electromagnetic spectrum could ever hope to detect them directly. An entirely different kind of sensing altogether was required, built on an entirely different branch of physics, to notice that this category of event was even happening. This serves as a powerful reminder that the electromagnetic spectrum, vast as it is, does not even represent the full totality of physical information available to be sensed. It represents one enormous category among what may be several distinct categories of physical signal, each requiring its own specialized form of detection, each expanding human awareness of the universe in a direction that biological evolution, focused narrowly on terrestrial survival, had absolutely no reason to prepare any organism for in advance. Interestingly, a small number of individuals experience something that hints, in a very different and far more modest way, at how flexible sensory categorization can become even without any external technology at all. Synesthesia, a naturally occurring condition present in a meaningful minority of the population, causes stimulation in one sensory channel to reliably trigger a consistent, involuntary experience in a completely different channel, such as a person who perceives specific musical notes as having a specific, consistent color, or a person for whom individual numbers or letters are permanently and vividly associated with particular hues, regardless of the actual color the number or letter is printed in. Researchers studying synesthesia through careful behavioral testing and brain imaging have found that these associations are not simply learned metaphors or creative habits of speech. They appear to arise from genuine, measurable cross-activation between brain regions that, in most people, remain functionally separate. And this cross-activation produces experiences that synesthetes themselves consistently describe as feeling every bit as real, automatic, and involuntary as ordinary color perception feels to anyone else. Synesthesia does not expand the electromagnetic range a person can detect in the way a thermal camera or a wearable magnetic sensor does. What it demonstrates instead is that the boundaries separating one sensory category from another inside the brain are not as fixed or as impermeable as they might intuitively seem, and that the specific architecture producing an ordinary, singular experience of color in most people is itself only one particular configuration among several that a functioning human nervous system is capable of producing. A small but genuine piece of evidence that the entire perceptual system, color included, is built rather than given, assembled by a specific arrangement of neural wiring rather than delivered as some fixed, universal, unchangeable feature of what it means to have a brain at all. The convergence of all these separate lines of investigation, biological, physical, technological, and philosophical, points toward a reframing of the entire question this investigation began with. The original framing treated narrow human perception as a kind of deficiency, a gap between the infinite richness of the electromagnetic field and the impoverished window through which any single human consciousness experiences it. That framing is not wrong, exactly, but it is incomplete, because it quietly assumes that more sensory information would automatically be better, that an expanded, unfiltered perception of the full electromagnetic spectrum would represent an upgrade rather than a burden. The evidence gathered from decades of neuroscience research, sensory substitution experiments, and comparative animal biology suggests something more complicated and, in its own way, more interesting than that simple assumption allows. Consider what would actually happen if a human nervous system, structured exactly as it currently is, suddenly gained unfiltered access to the entire electromagnetic spectrum rather than the narrow visible band it currently processes. Every object radiating heat would appear as a glowing presence. Every wireless signal, every cell tower transmission, every stray radio broadcast passing invisibly through the walls of an ordinary room would suddenly demand conscious attention, alongside the reflected visible light already providing information about shape, distance, and texture. The result would not be a richer, more complete experience of reality. It would very likely be an overwhelming, disorienting flood, an amount of simultaneous information vastly exceeding what any biological nervous system, built through evolution to process a specific, bounded range of inputs, could realistically integrate into a coherent, actionable picture of the surrounding environment fast enough to be useful for anything at all. This is precisely why the sensory substitution devices discussed earlier are designed the way they are, translating additional electromagnetic information into a slow, deliberate, learnable channel such as a vibration or a tone, rather than attempting to simply flood the visual system with raw additional data all at once. Even technology explicitly designed to expand human perception has to respect the same underlying constraint that shaped biological vision in the first place. A nervous system, however sophisticated, has a finite processing budget, and any sensory system, biological or artificial, has to make deliberate choices about what to include and what to leave out if it hopes to remain useful, rather than paralyzing. This reframes the narrowness of human perception not as an unfortunate accident or a regrettable limitation to be overcome as quickly and completely as possible, but as a functioning solution to a genuinely difficult engineering problem, the problem of extracting a small high-value, rapidly actionable signal from an environment containing a nearly infinite amount of raw physical information. Every nervous system that has ever evolved across every branch of the animal kingdom has had to solve some version of this same problem. And every solution that survived long enough to be studied today represents a different, workable answer to the same underlying constraint. The mantis shrimp's unusual visual system, the pit viper's infrared sensing organ, the migratory bird's magnetic sense, and the ordinary human eye's three-cone color vision are not ranked entries on a single scale running from worse to better. They are parallel, independently evolved solutions, each one tuned to the specific ecological problems facing a specific lineage, and each one representing a deliberate, evolutionarily reinforced act of filtering rather than failing to detect the full spectrum. Understanding this reframes the relationship between infinite electromagnetic reality and finite biological perception as something closer to a partnership than a limitation. A partnership in which the nervous system's job has never been to passively receive an accurate copy of the external world, but to actively construct a usable, simplified model of it, one specifically optimized for the tasks that actually matter to the organism doing the perceiving. Recognizing this does not make the electromagnetic spectrum beyond human vision any less real, and it does not diminish the value of the technologies and instruments built over the past 2 centuries to reveal it. If anything, it clarifies exactly what those instruments are accomplishing and why they matter. A radio telescope, an infrared space observatory, or a wearable thermal sensor is not correcting a biological mistake. It is extending a strategy that biology has been running successfully for hundreds of millions of years. The strategy of building specialized instruments to detect specific, useful slices of a far larger physical reality. Except now that strategy is being carried out deliberately, collectively, and with a flexibility no single evolutionary lineage, bound by the slow pace of genetic mutation and natural selection, could ever achieve entirely on its own. There is also something worth appreciating in the fact that this entire investigation, tracing the electromagnetic spectrum from Maxwell's equations through the retina and into the philosophy of subjective experience, is itself only possible because of the very perceptual system it examines. A being with no vision at all, or a being whose vision worked in some radically different way, would have arrived at an entirely different scientific history, would have discovered infrared and ultraviolet radiation through entirely different experimental routes, if it had discovered them at all, and would have built an entirely different intuitive relationship to the concept of color from the very beginning. Human science, as detailed and rigorous as it has become, was constructed by minds working through bodies equipped with this one particular, narrow, three-cone visual system, and every diagram, every wavelength chart, every carefully labeled illustration of the electromagnetic spectrum was ultimately produced by researchers translating their instrument readings back into a form their own narrow visible light vision could examine and understand. In a strange, recursive way, the very act of mapping the full extent of the electromagnetic spectrum has always depended on the narrow, biological perceptual system that map was designed to transcend. A reminder that even the most rigorous scientific investigation of perception's limits is still, in the end, being carried out by minds working within those very limits. None of this closes the investigation, because a great deal about the boundary between infinite electromagnetic reality and finite, conscious perception remains genuinely, actively unresolved, and it is worth being precise about exactly what current researchers still do not know. rather than allowing the confident tone of the established science discussed so far to create the impression that every question in this area has already been answered. The hard problem of consciousness, the question of why any physical process, however precisely mapped, is accompanied by subjective experience at all, remains as open today as it was when philosophers first articulated it clearly. And there is no scientific consensus on what kind of evidence would even count as a satisfying resolution to that question, let alone what the resolution itself might look like. Some researchers suspect the answer will eventually emerge from a deeper understanding of how information is integrated across large populations of neurons. Others suspect the question may be malformed in some way not yet fully understood, resting on hidden assumptions that will need to be revised before real progress becomes possible. Still others take the position that certain aspects of subjective experience may simply lie permanently beyond the reach of any third-person scientific method, no matter how sophisticated that method eventually becomes. This is not a case of researchers being close to an answer and simply needing more time and better equipment. It is a case of deep, ongoing, foundational disagreement about the basic shape of the problem itself. The practical question of sensory augmentation carries its own set of open uncertainties, quite separate from the philosophical puzzle of consciousness. While sensory substitution devices have demonstrated repeatedly and convincingly that the human nervous system is capable of learning to interpret entirely novel channels of translated electromagnetic information, researchers still do not fully understand the upper limits of this flexibility. It remains unclear how many additional channels a single nervous system could realistically integrate before running into fundamental bottlenecks in attention, working memory, or processing capacity. Bottlenecks that might have nothing to do with the electromagnetic spectrum at all, and everything to do with more general constraints on how much simultaneous information any brain, biological or otherwise, can meaningfully hold in conscious awareness at a given moment. It also remains an open question whether early exposure during childhood development, when the brain's capacity for plasticity is at its most pronounced, might allow for a far deeper and more seamless integration of expanded sensory channels than anything achievable in adulthood. A question that carries obvious ethical complexity alongside its scientific interest, since any research addressing it directly would require extraordinarily careful, long-term study of developing nervous systems rather than the shorter-term studies conducted with adult volunteers that have produced most of the sensory substitution results discussed earlier. There is also an entirely separate and increasingly relevant open question concerning artificial systems rather than biological ones, as machine learning systems and artificial sensors become more deeply integrated into daily technological infrastructure, from the sensor arrays guiding autonomous vehicles to the multispectral imaging systems used in scientific and industrial applications. A growing amount of electromagnetic information about the world is being continuously captured, processed, and acted upon by systems that have no biological nervous system at all, and therefore no evolutionary history shaping what counts as a survival-relevant signal worth prioritizing. These systems face an analogous version of the same filtering problem discussed throughout this entire investigation, needing to extract useful, actionable patterns from an overwhelming amount of raw electromagnetic data. Except without the hundreds of millions of years of evolutionary refinement that shaped biological perception toward specific, tested solutions. Researchers studying how these artificial systems choose to filter and prioritize information are, in effect, running a compressed, deliberately engineered version of the exact same evolutionary process that originally produced the human eye, except operating on a timescale of years or even months rather than geological ages. And the solutions these systems arrive at, sometimes surprising and counterintuitive even to the researchers who built them, are beginning to offer a new and unexpected point of comparison for understanding just how much of biological perception was shaped by genuine necessity versus historical evolutionary accident. Perhaps the most genuinely open question of all, and one that connects everything discussed in this investigation back to its opening framing, concerns whether there exists any meaningful sense in which a more complete perception of the electromagnetic spectrum would actually constitute a more complete understanding of physical reality in general, or whether the electromagnetic spectrum itself, vast as it is, represents only one layer among several equally important layers of physical information. As the earlier discussion of gravitational waves already began to suggest, if gravitational waves exist entirely outside the electromagnetic spectrum and require an entirely separate category of instrument to detect, it raises the further question of whether there might be additional categories of physical phenomena currently undetected by any instrument yet built, quietly surrounding every observer in exactly the same way the electromagnetic spectrum surrounded every organism on Earth for the entire span of evolutionary history before infrared and ultraviolet radiation were first identified in the early 1800s. There is no way to rule this possibility out from where current science stands today, and the history of scientific discovery, repeatedly revealing invisible categories of physical reality that no one previously suspected existed at all, offers a strong reason for genuine intellectual humility about how complete any current picture of the physical world, however sophisticated, is likely to actually be. What can be said with confidence is that the investigation into how biological perception relates to physical reality continues to be an active, well-funded, rapidly evolving area of research, drawing together neuroscientists studying the fine details of retinal processing, physicists refining the instruments used to detect ever more subtle categories of electromagnetic and non-electromagnetic signal, engineers building the next generation of sensory substitution and augmentation devices, and philosophers continuing to sharpen exactly what questions about consciousness and subjective experience can and cannot currently be answered by empirical methods. None of these separate lines of investigation are close to producing a final, settled picture. Each one continues to generate new findings, new techniques, and new open questions faster than the previous generation of questions can be fully resolved, which is, in its own way, exactly the situation any genuinely important area of ongoing scientific inquiry should be expected to be in. The photon perception paradox, in the end, is not really a paradox in the sense of containing a genuine logical contradiction. Maxwell's equations and the narrow biology of the human eye are not actually in conflict with one another. They describe two different things, operating according to two entirely different sets of constraints. One governed by the pure mathematics of a physical field extending without limit across every possible frequency. The other governed by the practical, resource-limited demands of keeping a specific organism alive long enough to pass its genes forward into the next generation. The apparent tension between them dissolves once it becomes clear that biological perception was never attempting to match the completeness of the underlying physics in the first place, and was never expected to. What remains, once that tension dissolves, is something quieter and, in its own way, more remarkable than a paradox, The recognition that every conscious experience of color, every glimpse of a sunset, every glance at a familiar object, is the end product of an extraordinarily specific, ancient, carefully filtered translation process, converting a boundless physical field into a small, useful, deeply human slice of reality, and at this narrow slice, rather than being a limitation to regret, is precisely what has allowed a species with a brain the size of a human brain to function, to survive, and eventually, through centuries of careful instrument building and patient observation, to look back and finally understand just how much larger the ocean of light truly is than the small window any single pair of eyes was ever built to see through, and to keep building the instruments capable of revealing more of that ocean, one invisible wavelength at a time, without ever fully expecting to reach its final edge, stepping back even further, past the specific mechanics of the human retina and into the broader evolutionary history of eyes themselves, reveals just how many independent times a light-sensing organ has been invented across the tree of life, and how consistently each independent invention converged on the same basic strategy of narrowing an infinite spectrum down to a small, manageable working range. Eyes are believed to have evolved independently dozens of separate times across different branches of the animal kingdom, ranging from the simple light-sensitive patches found in some flatworms, capable of little more than distinguishing light from darkness, to the sophisticated compound eyes of insects, built from thousands of individual repeating units, each capturing a tiny fragment of the surrounding visual field, to the camera-style eyes shared by vertebrates and, remarkably, by certain cephalopods, such as octopuses and squid, which arrived at a strikingly similar lensandrotan design through a completely separate evolutionary path, unrelated to the vertebrate lineage by hundreds of millions of years of independent history. This repeated, independent convergence on broadly similar solutions is often cited by evolutionary biologists as strong evidence that detecting and interpreting light provides such an overwhelming survival advantage that natural selection discovers workable versions of the solution again and again, whenever the right underlying biological materials happen to be available. What is particularly striking, given everything already established about the narrowness of the visible spectrum, is that every single one of these independently evolved eyes, across every one of these separate evolutionary lineages, converged on detecting light within roughly the same narrow band of wavelengths. The same band already identified earlier as corresponding closely to the peak output of the sun's own energy curve and the clearest transmission window through Earth's atmosphere. An octopus eye and a human eye, separated by an evolutionary distance so vast that their most recent common ancestor likely had no image-forming eye at all, nonetheless ended up tuned to almost exactly the same portion of the electromagnetic spectrum, not because of any shared genetic instruction inherited from a common ancestor, but because both lineages were independently solving the exact same physical optimization problem posed by the same star and the same atmosphere, and arriving, unsurprisingly, at very similar answers. This convergence offers a particularly clean piece of evidence supporting the earlier argument that the visible spectrum was never an arbitrary biological accident. It is closer to being the predictable, almost inevitable answer to a well-defined physical optimization problem, an answer independently rediscovered again and again throughout the history of life on this particular planet. The specific number and type of photoreceptors carried by any given lineage, however, turns out to be shaped far more by particular ecological pressures than by any universal biological rule, which helps explain why, despite this broad convergence on a similar general range of wavelengths, the fine details of color vision vary so dramatically from species to species. Many mammals, including dogs, cats, and most other placental mammals, aside from primates, carry only 2 functional cone types rather than 3. A limitation researchers believe traces back to a period deep in mammalian evolutionary history when early mammals were small, nocturnal creatures living in the shadow of dinosaurs, active primarily at night when color vision provides relatively little survival advantage compared to the ability to detect faint light and movement in near darkness. Under those specific ancestral conditions, maintaining a third cone type would have represented a biological cost with little corresponding benefit, and natural selection allowed that third cone type to be lost. It was only later, within the primate lineage that eventually gave rise to humans, that a third cone type re-emerged, most likely because the ability to distinguish ripe reddish or orange fruit from green foliage against a backdrop of green leaves provided a strong enough survival and feeding advantage in a diurnal, fruiting primate to justify redeveloping the additional biological cost of a third distinct photoreceptor type. This particular piece of evolutionary history means that human trichromatic color vision is not a baseline, default feature of mammalian biology at all. It is a comparatively recent, specialized evolved specifically to solve a foraging problem faced by fruit-eating ancestors moving through forest canopies, layered on top of a far more ancient and more common 2-cone mammalian baseline that the majority of mammal species alive today still carry, considered together with the discussion of the mantis shrimp, the pit viper, and the magnetically sensitive bird earlier in this investigation. This evolutionary history of the eye reinforces, from yet another angle, the same central conclusion running through the entire narrative. Perception is not handed down from some universal biological template that all life shares equally, gradually approximated with more or less success by different species. It is repeatedly, independently constructed, each time shaped by a specific combination of available genetic material, ecological pressure, and evolutionary history, producing a wide and genuinely surprising diversity of working solutions to the shared, underlying challenge posed by an electromagnetic environment none of these solutions ever needed to capture in full. Bringing this back to the wearable and neural technologies discussed earlier, the pace of development in this specific area has continued to accelerate in recent research cycles, with newer generations of sensory substitution and augmentation devices, increasingly focused not simply on proving the basic concept works, which earlier research has already established fairly conclusively, but on refining exactly how much additional information a human nervous system can comfortably integrate without triggering fatigue, distraction, or a degraded ability to process the ordinary visible light information a person still relies on for the vast majority of everyday tasks. Some of the most recent wearable prototypes have moved away from constant, always-on translation of invisible electromagnetic information, instead offering the wearer deliberate control over when an additional sense is active, treating expanded perception less like a permanent replacement for ordinary vision and more like an optional, situationally useful tool that can be switched on when relevant, such as when searching for a heat leak in a building's insulation, or checking for unexpectedly strong wireless signal congestion in a crowded space, and switched back off the rest of the time. This design shift reflects a growing, hard-won recognition among researchers in the field that expanding, The range of what a person can technically detect is only genuinely useful if it can be integrated without overwhelming the exact same finite processing budget that has constrained biological perception. Since the very first light patch appeared on the very first simple organism, hundreds of millions of years before anything resembling a modern eye, let alone a modern nervous system, had ever come into existence. Modern spectral imaging, carried aboard satellites, meanwhile, continues to refine humanity's collective, technologically mediated view of the invisible ocean discussed at the very beginning of this investigation, with newer generations of instruments capable of resolving increasingly fine distinctions across the electromagnetic spectrum, distinguishing not merely between broad categories like infrared and ultraviolet, but between narrow, specific bands within each category, each one carrying its own distinct signature tied to particular physical or chemical processes on the ground or in the atmosphere below. Agricultural monitoring now routinely relies on specific narrow infrared bands sensitive to chlorophyll content, allowing researchers to detect crop stress from orbit long before any visible sign of wilting or discoloration would be apparent to an unaided human eye standing directly in the field itself. Atmospheric monitoring relies on other narrow bands sensitive to specific trace gases, allowing researchers to track pollution plumes, volcanic emissions, and shifting atmospheric chemistry with a level of detail that would have been entirely unimaginable using only visible light photography. Each of these narrow, specialized bands represents another small slice of the same electromagnetic ocean introduced at the beginning of this investigation. Another reminder that the gap between the infinite mathematical reality described by Maxwell's equations and the narrow biological reality of any single human eye continues to be bridged, patiently and incrementally, not by changing the underlying biology of human vision itself, but by building an ever-expanding collection of specialized instruments, each one designed to see exactly the small, specific slice of that vast invisible ocean that biology alone was never equipped to reveal. There is a final thread worth pulling on before drawing this investigation to a close, one that connects the deeply personal, subjective experience of seeing color back to the largest possible scale imaginable, the scale of the observable universe itself. Every photon of visible light that has ever struck a human retina began its journey somewhere else, whether reflecting off a nearby object only a fraction of a second earlier, or traveling for millions or even billions of years across the vast emptiness of space before finally arriving at the exact location and the exact moment necessary to strike a single cone cell and trigger the cascade of chemical and electrical events that eventually produces a conscious visual experience. Starlight visible to the naked eye on a clear night has, in many cases, been traveling since long before any human civilization existed, sometimes since before the sun itself finished forming, meaning that the narrow three-channel biological instrument sitting behind a human eye is not simply sampling a local, immediate environment. It is intercepting an almost unfathomably ancient stream of energy, filtering it down through the exact same three-cone bottleneck already described in detail, and converting the tail end of that ancient journey into the felt, immediate experience of a single point of light against a dark sky. This framing does something useful to the entire investigation, because it makes clear that the photon perception paradox is not simply a story about the limits of human biology in some narrow, self-contained sense. It is a story about the relationship between an almost incomprehensibly vast physical universe and the small, specific, evolutionarily shaped instrument any conscious observer happens to be equipped with, wherever and whenever that observer happens to exist. The same basic tension, an infinite field of possible information reduced to a narrow, useful slice by whatever detector happens to be available, would apply equally to any hypothetical observer anywhere in the universe, biological or otherwise, provided that observer evolved or was constructed under some set of practical constraints on energy, processing capacity, and available time. There is no reason to expect this tension to be unique to Earth, or unique to carbon-based biology, or unique to the specific evolutionary history that happened to produce the human eye. It appears to be a much more general feature of what it means to be any kind of finite observer embedded within an infinitely detailed physical universe, forced by the sheer scale of that universe to make constant, unavoidable choices about what to notice and what to let pass by entirely unregistered. Framed this way, the narrow window of human color vision stops looking like an isolated biological curiosity and starts looking like a specific, well-documented example of a far more universal principle, one that applies just as much to a satellite instrument tuned to a particular infrared band, or a gravitational wave detector tuned to a particular pattern of space-time distortion, as it does to a cone cell in a human retina tuned to a particular range of visible wavelengths. Every instrument capable of gathering information about the universe, whether biological or artificial, ancient or newly built, operates by making a deliberate or evolutionarily inherited choice about which small portion of an effectively infinite range of possible signals is worth capturing. And every act of perception, in this broader sense, is simultaneously an act of profound, unavoidable omission. Understanding color vision in this light transforms it from a narrow topic in sensory biology into a specific, deeply personal illustration of one of the most general and unavoidable features of observing anything at all, anywhere, at any scale, a feature that will likely remain true for any conscious or technological observer that ever exists, no matter how sophisticated its instruments eventually become, and no matter how much further into the invisible, electromagnetic ocean those instruments eventually manage to reach. What remains, after tracing this arc from the pure mathematics of an oscillating field through the chemistry of a single retinal molecule and outward again toward the largest structures in the observable universe, is not a tidy resolution but an invitation to keep looking more carefully at something most people spend their entire lives taking completely for granted. The next time an ordinary sunset produces its familiar wash of orange and red, or a familiar object catches the light in a way that feels simple, immediate, and complete, it may be worth remembering everything actually happening underneath that simplicity, an ancient, elegant physical wave, stripped down through hundreds of millions of years of evolutionary refinement into 3 narrow chemical channels, reconstructed moment by moment into a private, felt experience that science can trace in remarkable physical detail, while still not fully explaining why it feels like anything at all. The universe surrounding every observer remains exactly as vast, as energetic, and as electromagnetically saturated as it has always been. What continues to change, slowly and unevenly, through careful instrument building, patient research, and an ever-expanding willingness to question what counts as a complete picture of reality, is how much of that vast, ancient, invisible ocean any given observer, biological or otherwise, is currently equipped to notice. That gap between the infinite ocean of electromagnetic possibility and the narrow, hard-won window through which it is currently perceived is not a flaw waiting to be corrected so much as it is the honest, ongoing condition of every finite mind trying to make sense of an unfinished universe. One careful measurement, one new instrument, and one patiently reconciled paradox at a time. It is a strange kind of comfort, in the end, to realize that the very act of asking why perception is so narrow already requires a mind capable of stepping outside its own narrowness, just far enough to notice the boundary at all. A small, recursive miracle performed quietly every time a curious observer looks up at a familiar sky and wonders, for a moment, just how much more of it might still be waiting to be seen. Every instrument built to look further into that invisible ocean, and every future instrument not yet imagined, will simply be the next iteration of the same fundamentally human project that began the moment a curious mind first placed a thermometer just past the visible edge of a rainbow and noticed that something invisible was there all along, quietly waiting to be measured. That is, ultimately, the quiet reconciliation at the heart of this entire investigation. Maxwell's perfect, infinite wave equations and the imperfect, narrow biology of a single human eye were never actually opposed to one another, because one describes what exists and the other describes what a particular kind of finite creature, shaped by a particular star, a particular atmosphere, and a particular evolutionary history, needed to notice in order to survive long enough to eventually build the instruments capable of describing the rest.